Let's see, last time we were talking more about multiplicative norms, and so here's where we're at. Let me just sort of recap what we have so far. So if n is square free, so remember that means that it's not divisible by the square of any prime. So if it's square free and n not equal to 1, then there's a few things that we know. So first of all, we want to study rings of this form right here, right? Z bracket square root of n. And so capital N, which goes from Z bracket root n to Z, given by so the n of a plus b root n equals a squared minus nb squared. This is a multiplicative norm on z bracket root n. There was a key, we went and proved this last time, and there was a key point where we really needed square freeness to verify that it's a multiplicative norm. Now, it turns out then we also verified that the norm of an element a plus b root n equals 1 if and only if a plus b root n is a unit. And what we, I need absolute value here. And we know, so always if you have a norm, right, a multiplicative norm always takes a unit to 1, plus or minus 1, right? So absolute value. But when it goes the opposite direction, then you have this consequence right here that, I should say if. So if the absolute value of the norm of a plus b root n is prime, then a plus b root n is irreducible. So when we have item 2 directly implies this right here. So when you have the situation where only units get sent to plus or minus 1, then you can use the multiplicative norms to detect irreducibles. Okay, and so I want to do some more examples, and in particular, we want to show. So let me just say, warning. The converse is false. I should say the converse of 3 is false, and this next example will show that. And so the point is, just because you have an irreducible, right? So if it's irreducible, that does not necessarily mean that it's prime. And so let's look at this example right here. So I'm going to look at z bracket square root of minus 3. Remember, we're allowed to put any integer here, and then we define what this means, right? It means, well, it means the elements look like this, right? Which means that we can have imaginary parts in here. These are all subrings of the complex numbers. So in z bracket square root of minus 3, the norm of a plus b square root minus 3, that's going to equal, so it'll be a squared plus 3b squared. One thing to notice, right, so that's always going to be greater than or equal to 0 now. Right, so we can't have negative values in our norm in this situation right here. So what I want to do, let's consider the element, so I want to look at 1 plus square root minus 3. Now, if we compute the norm, so the norm of 1 plus square root of minus 3, that's going to equal 1 plus 3, which equals 4. Which is not prime, right? So let's just point that out, of course, which is not prime. So now, suppose that 1 plus square root of minus 3 is equal to x times y. What I'm going to do is I'm going to show that 1 plus square root of negative 3 is an irreducible, even though the output under the norm was 4, which is not prime, right? And so that's going to show that the converse is false. Okay, so suppose that our element 1 plus square root minus 3 equals x times y. What I want to do, I need to show then that either x or y is a unit. That will allow me to conclude that, that it's an irreducible. So let me finish my sentence here. So suppose this factors as this equals x times y for some x and y in z bracket square root minus 3. Now, what I want to do is say, okay, what would happen if the norm of one of these is equal to 2? So then we would have, so let's say like this, so then 4 is equal to the norm of x times y, because x times y is this, which has norm 4. And because it's a multiplicative norm, so here's where the power of multiplicative norms comes in, it allows you to factor. Okay, so then what we have is this, right? The norm of x times norm of y has to equal 4. So now, note that a squared plus 3b squared equal to 2 is impossible, right? What are your options here? Well, you could have a equal to 0, b, a equal to 0, b equal to 0, a equal to 1, b equal to 1. In fact, as soon as both a and b get larger than 1, or then it's all over, right? You can't get something equal to 2. It's going to be too big, right? So this is impossible. And so what does that tell us then? It tells us that the norm of x, the norm of y could not be equal to 2, which are factors of 4. And so what does that mean? All right, so this is impossible. And so the norm of x has to equal 1. Absolute, well, it's always greater than 0, so I don't need to say absolute value here. So, or norm of y equals 1. And what do we know? That means that x is a unit or y is a unit. And so, x is a unit or y is a unit. What does that tell us then? Well, anytime we factor this element as x times y, one of the two has to be a unit, so we can say therefore 1 plus square root minus 3 is irreducible. So that's what I was talking about, the converse. What we have is we have an element that is irreducible even though its norm is not a prime number, right? So the converse is not true. It only goes in one direction. If you know that the absolute value of the norm is prime, then you can conclude that it's irreducible, but not vice versa. Okay, so now I want to make a claim. So still working within this same example right here, I want to claim that 1 plus square root minus 3 is not prime. And for the proof, goes like this. So well, okay, so let's say it like this. So note that 1 plus square root minus 3 times 1 minus square root minus 3, what's that going to be equal to? Well, that's going to be equal to 1 plus 3, so that's equal to 4. And so our element 1 plus square root minus root 3 divides 4. Of course, 4 is equal, in fact, let's just say this, 4 is equal to 2 times 2. So to show that it is not prime, what I would need to do, I should dot in there, 2 times 2, is if I can show that it does not divide 2, then we conclude that it's not prime. So suppose that 1 plus square root minus 3 does not divide. Oh, whoops, sorry, not that does not. Suppose that it does divide. So suppose that this divides 2. Okay, so what does that mean? It means that 1 plus minus root 3 times some element equals 2. What do I want to call it? I'm going to call it a plus b minus root 3. All right, so then we have that 1 plus square root minus 3 times a plus b square root minus 3. And let's actually write out who this is. This is equal to, so I'm going to have an a plus 3b, minus 3b, so a minus 3b plus, then it's going to be a plus b, let's see, there's a b and there's an a, yeah, so plus a plus b root minus 3 has to equal 2 for some a and b in z. Right? If it divides 2, that means that this guy is a multiple, or 2 is a multiple of this guy right here, which means that this times some element has to equal 2. Okay, well, so now just comparing, we can see, right, there's no imaginary part on this side, so that tells us that a plus b has to equal 0. And then a minus 3b has to equal 2. So it follows that a minus 3b equals 2, and a plus b equals 0. And let's see, what would that tell me? If I subtract one from the other, that's going to give me that. So in fact, let's actually do the solution here. So a minus 3b equals 2. You don't need to write this down. A plus b equals 0. I'm going to subtract. That's going to give me negative 4b equals 2, which means that b has to equal minus 1/2. We know that that can't happen. All right, we have to have integer solutions. So you don't need to write this part down. You can just say check, or I'll say check, that this system has no integer solutions, and so it's impossible for 1 plus square root of 3 to divide 2. So that's our contradiction there. And so conclusion, or we'll say therefore, 1 plus square root minus 3 does not divide 2. So we have that 1 plus square root of minus 3 divides 4, but it does not divide its factors. That forces us to conclude that 1 plus root 3 is not prime. So conclusion, 1 plus square root minus 3 is not prime. Okay, so what did we show here? In this example, we have an element that's irreducible but not prime. But we had a theorem a little while ago that says in a principal ideal domain, irreducibility and prime are the same, right? They're equivalent. If it's one, it's the other. Of course, prime always implies irreducible, but not the other way around. And so now we have an example of an irreducible that is not prime, and this also shows, so let's say as a consequence, z bracket square root of minus 3, it can't be a principal ideal domain, so it is not a PID. Okay, so I want to do one more fun example. In this case, I want to work in z bracket square root minus 5, and I want to consider the number 46, which of course we can factor as 2 times 23. But in z bracket square root of minus 5, it also factors as 1 plus 3 times square root of minus 5 times 1 minus 3 times square root of minus 5. So what we have here is potentially 2 different factorizations for the same number. So my claim is that all 4 of these numbers are irreducibles in z bracket square root minus 5, right? 2, 23, and 1 plus or minus 3 square root minus 5. So claim all 4 factors above are irreducibles in z bracket square root minus 5. And so for the proof, all right, so let's look at 2 first and show that it's an irreducible. Right, so suppose that 2 is equal to x times y for some x and y in z bracket square root minus 5. All right, what I need to do is show then that x is a unit or y is a unit. That'll allow us to conclude that 2 is an irreducible. Now, okay, so then I'm going to take the norm. So then, okay, so the norm of 2 is 4. That's equal to the norm of x times y. And because we've got a multiplicative norm, that's norm of x times norm of y. Okay, now what I want to do is I want to show that the norm of x or the norm of y has to be 1. So what if it's not, if one of them's 1 and one of them's 4, then we conclude that we've got an irreducible. If both of them are 2, then something goes wrong, right? So suppose, x, norm of x equals 2. Well, so then, if we think of x as a plus b times square root of minus 5, so then what we have is a squared plus 5b squared, right? is equal to, oh, right, sorry, norm of here is equal to 2, but that's impossible, right? There's no integer solutions for some, so we'll say some A and B and Z, which is impossible. And here I'm just eyeballing this, right? Think about A squared and B squared. If you plug integers in here, right? As soon as A and or B gets greater than 1, it's all over. In fact, if B is 1, can't happen. So that means B has to be 0, and then of course A squared equal to 2 does not have integer solutions also. Okay, so thus norm of x equal 2, or thus norm of x is not equal to 2. And so norm of x equals 1, or norm of x equals 4. If norm of x equals 1, then x is a unit. So if norm of x equals 1, then x is a unit. If norm of x equals 4, that would force norm of y equal to 1, which would mean that 1 is a unit, y is a unit. So if norm of x equals 4, then y is a unit. Okay, so that tells us then, so therefore 2 is irreducible. So now I want to show that 23 is irreducible. So we'll do the same thing. So suppose 23 equals x times y for some integers, no, not integers, sorry, elements of z bracket square root minus 5. So then we have 23 squared. That's going to be the norm of x times y, which is norm of x times norm of y. So now, if we can rule out the possibility of norm of x equal 23, then we're done for the same reason as over here. So if norm of x equals 23, then there exist integers a and b such that a squared plus 5b squared equals 23. And then you can just check that no such a and b exist. So check that. And this is just, okay, so what can a be? 1, 2, 3, 4, 5. No, as soon as you hit 5, you're too big. So a can be 1, 2, 3, 4, or 5. B can be 1, 2, 1 or 2. If it's 3, we get 9, 5. Yeah. So 1 or 2. And so you just look at, just mix and match those and verify that you never get 23. So let's check that that none exist. That's a contradiction, and therefore the norm of x and the norm of y can never equal 23. So thus, norm of x equal to 23 is impossible. And then for the same reasoning as before, right, so say therefore, x or y is a unit. And so our conclusion is that 23 is irreducible as well. Okay, so now we just need to think about, what was it, 1 plus or minus 3 times square root of minus 5. And one of those is a homework problem. So in homework, you will show, maybe you've already done this, you will show that 1 plus 3 square root minus 5 is irreducible. And the argument that you use for the plus will be the same as for the minus, so a similar argument. Shows that 1 minus 3 square root minus 5 is irreducible. Okay, so now we have 46 expressed in two different ways. Well, okay, I shouldn't say two different, but yeah, they're essentially two different ways as products of irreducibles. Now, when I say two different ways, what we really mean, if we want to think of them as truly distinct factorizations, then nobody should be associates of each other, meaning 2 should not be an associate of 1 plus or minus 3 root 5, or minus root 5. Same with 23. Okay, so now we need this observation. So let's say note that the units of z bracket square root minus 5. Okay, so those are going to be exactly the elements whose norm is equal to 1. So these are the units of z are the elements a plus b square root minus 5 such that a squared plus 5b squared equals 1, right? The elements whose norm is equal to 1. Well, the only integer solutions to this equation are a equals plus or minus 1. So only solutions are a equals plus or minus 1 and b equals 0. So that means that the units of z bracket root minus 5 are only the numbers plus or minus 1. So units of z bracket square root minus 5 are plus or minus 1. So now remember what we have, right? We have 46 equal to 2 times 23 and equal to 1 plus 3 square root minus 5. 1 minus, you don't need to write this down, 3 square root minus 5. So now clearly plus or minus 1 times 2 doesn't give us either of those. Plus or minus 1 times 23 doesn't give either one of these. So they're not associates. Right? So it follows that 2 and 23 are not associates of 1 plus or minus square root minus 5. So what does that mean then? We have distinct factorizations of the number 46 inside z bracket square root of minus 5, which tells us what? It tells us that this ring is not a UFD. All right, so therefore, z bracket square root minus 5 is not a UFD. Okay, and that's where I want to leave it off. So we will see you next time. Okay.